All right, so this is Section 3, Lecture 16, Generative Base Classifier, Module 1. And I will reuse some of my last year's recording, and we are in the Generative Classifier group. Let's get started.
All right, so we categorize the classification algorithms into three kinds. The first kinds we covered is instance-based classifiers. In fact, there's no model here, right? So it's just there's no model, there are no parameter. The only thing is hyperparameter, number of neighbors to pick. So you're using the training observations as part of the model. And then the second category, the bigger category we covered, is discriminative classification. The logistic regression, support vector machine, and deep neural nets, they all follow this category, and just they're all modeling the y conditional x, and more specifically, if it's a probabilistic formulation, it's the logistic regression and neural nets. You're using a probabilistic prediction to model the y given x, but SVM using more. There's no probabilistic formulation in that classification decision. And then in the generative model, which is what we're going to cover today, is using a probabilistic formulation to perform classification. And this is the roadmap. Again, we're in the base classifier, when you're using the probabilistic models to try to perform classification, and then through the MAP rules, those type of classifier are called all under the umbrella of base classifier. Okay, so just a little bit of review, because we already covered, right? So the base classifier uses MAP rules, maximal A posterior rules, to perform classification. So the most important is you have to be able to estimate PC conditional x. So here C is our output variable, x is our input variable vector. So because we normally have multiple input features, that makes a random variable vector. So the whole fundamental is I'm using PC conditional x, and whoever give me argmax, here the arg is that specific classification values, give me the largest. I'm predicting my classification label as the one give me the largest conditional probability. So this is the MAP rule. In the testing phase, you're really just trying to find the one, give you the largest, C star, and then and then in the training phase, actually this is what you use in the testing phase, and this in the end, this is how you're using to perform testing or perform inference. And the learning, while you're learning this type of model, the fundamental is how do you estimate this from data? So what do you even mean estimate this from data? And the variations of the base classifiers, it's about what is this probability distribution, what probability model you're using to represent this. And so there are two bigger kinds, and we can separate base classifiers using into discriminative base classifier or generative base classifier. The differences is the discriminative classifiers directly modeling PC conditional on x. So your input is x1 to xp, your model gives you directly that probability, this conditional probability is C over x. And then the multi-class logistic regression, it's for logistic regression, it's for the binary cases, which exactly modeling this. If you still remember what is the multi-class, is that softmax function, right? The softmax provide you is P yi equals to 1 equals to E z I over summation I from 1 to maybe capital L, there are total L labels, e to the z to maybe j, yeah, here's j. Yeah, so the predicted yi, yeah. So, and this is actually, that's the probability. I should have x conditional. Yeah, so this is exactly what softmax function gives you, right? And this is the probability formulation, and that probability is just a parameterized form related to the x variables. And this is a Martinoli distribution. This is a Martinoli distribution. A logistic regression uses a Bernoulli distribution to model. And it's just the parameter of that Bernoulli distribution is a function of x. All right, so we already had this learned very nicely. Then let's see the other regime. What is the generative-based classifier? So generative-based classifier, instead of directly modeling P, C conditional on X, it modeling P, X conditional on C. So it had the model, it's the generative classifier. If you have C1, C2 onto CL, L different classes, you're going to have L different models. It's how do the first class, CL, C1, generating my example X. How do the second class, C2, generating my X? How do the L class generating my X? So this is the model it's modeling. This is the probability it's modeling. But this is not P, C conditional X, right? To be able to use MAP rule, what I need to have is P, C sub I conditional X. And you might already still remember the whole assumption there is it's easier to directly estimating P X conditional on C, and then we're using base rules from P X conditional on C to derive PC conditional on X. So if it's hard to directly estimate from data, because our P C conditional on X is a conditional probability, right? And we use base rule to estimate this from P X conditional C. Okay, I hope you still remember this base rule. And this is the base rule. So we are just assuming this is easy to be directly estimated from data, and then we are using this to derive PC conditional X. Because you need this to use the MAP rule to decide which one is the max. So the rule is, again, C star equals to argmax C I P C I. Say from the set C1, C2 onto CL. Okay, question about this. This is the fundamental idea of generative-based classifier. All right. Yeah, so that's the base rule. And if you look at this, I want to estimate this, right? And then performing, and then that means I need to estimate this and also estimate this. And assuming those are easier to be calculated from data. The only thing, I mean, if I want to get a precise PC conditional on X, I also need to have PX in the denominator, right? However, if you see, I'm trying to do argmax, right? So the whole MAP operation is argmax. So whoever is the max C, it's the argmax operation, right? And to performing argmax on this, equivalent to perform on this, the denominator is not related to C at all. And also, no matter what CI is there, this is a shared value in the denominator, which means it doesn't change the ordering of C1, C2, or at all. That's why we don't need it if we care it's only the max operation. And that's the reason why when you normally see in the generative base classifier, what you truly calculated is only the denominator part. And you do not need the denominator because this doesn't change the argmax operation at all. It's proportional. The number here is proportional to the argmax operation is proportional to this. So that's why we don't need to calculate the denominator px. And then the only thing you need to calculate in the generative base classifier is px given c and also pc. Okay, so try to remember this, and this is how you do the calculation, and then you need to estimate from data to get this x congruency and also PCI. All right, and then you just use the PX congruency times PC, multiplying them together. And then for a specific x that you care, maybe on the future data, if you have the ability to represent this, and then you just perform argmax operation, you're going to go get the best classification. Whoever give me the best probability is the classification label I'm going to predict. And each one of them is a separate model. This first generative model is conditional on C1, it's generating x. The second generative model is conditional on C2, the third until the last, CL. They all generating X samples, but from different generative model. This sounds pretty weird for now, but when we do a concrete calculation, it will be very, very apparent. All right, so I hope you still remember this and understand this. Just to summarize, discriminative classifier directly modeling PC conditional X, generative classifier modeling the data from PX conditional C times PC, and they both use argmax operation on the C. Okay, so now let's see, this is your training data. Assuming we're given a training data like this, which you already had in the printout paper. So, and then the whole thing is, what do I need? What do I mean training in this? Assuming all the variables here are Machineulli variable, just discrete variables. So this is my x1 variable. This is x1, x2, x3, x4, and c. So the base classifier, the whole important idea is you're assuming, I hope you can read, every feature variable and also the output variables are random variable. So here I assume C, let's see, C variable, I assume it to be a Bernoulli distribution. And there are how many possibilities? It's only yes and no, right? So I'm going to switch to the next page and now look at your printout paper. Okay, so I have x1 variable, x2 variable, x3 variable, x4, and c. So this is what I have. And they are all random discrete variables. So how many possible values for the classification, the output variable? Only 2, right? Yes and no. And in fact, this is C1, this is C2. And then how many random variable, so for the first random variable x1, how many possible values? So sunny, overcast, and rain, right? There are only 3. SOR, let's write it as SOR. SOR. Okay, and then for the x2, we have HMC, right? Hot, mild, and cool. HMC. And for the x3 is HN, high, normal. There's only 2. For the x4, there's weak and strong. There are only 2. Yes. Okay, so these are their possible values. So just keep this in mind. Let's see. We already said I want to estimate the Px condition on C, right? So what do I mean Px condition on C? So how many x I need to figure out for the future data? Whatever that's an x, I can figure out Px condition on C. So in the end, to train the data, I need to figure out Px on C, right? x1, x2, x3, x4 on C, and also PC, right? So in the training phase, I need to estimate them from data. It's easy to estimate PC, right? Because there are only 2 cases. C equals to yes, and C equals to no. Okay, so what is PC equals to yes from this table? So there's a total of 14 cases, right? And it's a Bernoulli variable, right? Whenever it's Bernoulli variable, its probability of head is number of head over all the number of cases. So here, let's treat yes as the head. So how many yes I observed? 9. And in total, I have 14, which makes it pretty easy, is the number of times I see yes over all the possible observations, number of training size, which is 9 over 14. And the PC equal to no is extremely easy because 1 minus P, yes, right? It's 5 over 14. All right, so now I have the PC part. I need to estimate the second part is this. So how many combinations I need to know for all the possible future data I can give P this given this. Given the C, for all the possible situations, I need to have 2 cases. One C equals to yes or one C equal to no, right? Let's just give an example. In the end, I just need to count. I need to count this combination. This is a combinatorial set, right? How many this appears, this combination appears over all the training data? One conditioned on a specific C. And that's exactly let me give you an example. X1 equals to S, X2, let me look for a one actually exists. H, and X3 equals to H, X4 equals to weak, conditional on C equals to maybe no. So how do you calculate this from the training data? So what I had is SHHW, condition on no, right? You observed it how many times? It's really that observation. You observed it, this combination. You observe SHHW and no. How many times? Actually, in your table, one time. And then over what? How do you get this probability? We're assuming this is also a Martinelli, it's a discrete random variable. This combination is a discrete random combination. Condition on C equal to no, right? Which means my denominator is the number of times no. Right? Yeah, it's the number of times you observe the no, which is 1 over 5. I think it's 1 over 5, right? 1, 2. Yes, it's 1 over 5. Oh, good. Okay, who has question about this process? And then, because I have to do this for all the possible combinations of each possible values for each random variable, how many do I need to estimate from data? How many cases of this do I need to estimate from data? It's combinatorial of all the possible combinations of the values from x1, x2, x3, x4, and then condition on the no or yes, right? So this is 1 over 5, but also I need to estimate the other. This is 1 over 5. And I also need to estimate x1 equals to s. Let me do, it's a little bit harder to write on the bottom, so go to s. x2 equals to h. x3 equals to h. x4 equals to w. Condition on c equals to yes. So what is this from this table? The same combination, the same feature combination, but now it's yes. It should condition on yes. SHHW, right? Do we have SHHW on the yes? Actually, no. We don't have SHH in the yes cases, which makes this calculation as 0 over 9. Okay, so this just gives you a flavor of what do I mean estimating this type of discrete random vector from the data when there's a class variable I want to predict. So how many cases I need to estimate this type of cases? It's actually very easy to do the calculation, right? So the first X has 3 kinds. The second X has 3 kinds. The third has 2, 2, and then 2. So the number of whole that cases is sorry, it's kind of flashy. It's total of 72. This is actually our parameter to estimate. So this is the model of a generative-based classifier. This P, whatever combinations, conditioned on the C, each C, and this is the parameter you need to estimate from the data. And this is the parameter of your model, this generative-based classifier model. Question about this. This is very fundamental, and this is the key. So this is the training phase, right? In the training phase, you really just estimate. In fact, this uses the assumption called this is a discrete Machine'Learning distribution. Its MLE parameter is the counts over it's this count. So the number of cases you preserve over all the number of cases. And that's the classic MLE solution for Machine'Learning distribution. All right, so this is just a more, it's in the end, I try to more concretely do X2, X3, 2 cases, X4, 2 cases, X1, 3 cases, and C. All right, this is the 1/9, and then 0/9. I try to show you almost the same. You just directly estimate from data. And there's a total of 3 times 3 times 2 times 2, then times 2 number of parameters to estimate, plus 2 more, which is the PC equals to yes and PC equals to no. It all sounds pretty complicated, but in fact, this is your model. The model essentially is a lookup table. And the lookup table is, so the first case is PC, PC1, and PC2. This is exactly the PC1 and PC2. And we have only 2 C here. And then the X given on C is, so this is condition on the C1, this is condition on the C2, and this is all the combinations. You need to have all the possible combinations. So when you have sunny, hot, I mean, let's just show one. It's really just enumeration. There's no trick at all. Just enumerating all the possible combinations among the values. So for this case, you just have weak, strong, and then with the high, and then you move the high to normal, and this has weak, strong. It's just enumeration of all the cases. And this is a lookup table of conditional probability. And that's how you get, or either you're just counting how many cases this combination exists. One for the yes cases, you put counts here, and over all the possible yes cases. And how many of this combination exists in that training table for the no cases, and you put a count here, and you put the number of no cases as the denominator. This is how you get the probability, that conditional probability. And then how do you use it? When you use it is when there's a future data, assuming, let's just give you a case, maybe, I think I give you a case is SCH, and you really just do lookup. What is in that lookup table you learned from the training data? This is the future data. What is the corresponding SCHS condition on the yes, what is this probability from that table, and times P yes, and then what is this combination, condition on the no, that probability from the previous table, the no table, and then times P C to the no. And then for these two calculated values, which one is bigger, and then you assign the classification as the one give you a bigger probability. So how many features do I have here? Four features, right? And how many combinations do I have? Oh, I already calculated. It's the 3 times 3 times, yeah. So, yeah. So let's use extreme case. If this is for English dictionary, which is actually your homework 5. The x1 to xp is all the words. So what is p here, roughly? The p, so the p is roughly the number of is this p. P is about 30,000. Okay, so assuming there's only two possible values for each x1 until xp, exist or not exist, right? You can describe your articles always using, is that word exist or not? How many probability you need to get in that case? First, there are two combinations, exist or not. Second word, exist or not. Third word, exist or not. Until the pth word, exist or not. So how many parameters, assuming I'm predicting sentiment thumb up or thumb down, it's a positive or negative. So this is my x1 to xp. And my y, my c is good or bad, sentiment, good or sentiment. Yeah, I can write a thumb up, although I think the draw less, up or down. Yeah, let's do that. Up or down. So how many parameters do you need to estimate for this case? Use the same calculation like this lookup table. 2, 2, 2, 2, which means 2 to the p, and then times 2, right? Assuming there's total L parameter, L class labels. This is the size of that lookup table you have to estimate. Okay, so I think you know what's 2 to the p, right? 1p equals to 20. What is 2 to the p? 2 to the 20 may be feasible. 2 to the 30k, is it even possible or not? But think about it. 2 to the 30k. There's no way. But I'm just trying to show you, but this is one current solution. And there's no way to calculate on the fly. That just to tell you first, right? It's a huge number of things to memorize. And also because of this, we're going to do some kind of simplification later. But still, with 2 to the p, if p equals to smaller than 20, I think it's still feasible. Yeah, smaller than 20, 2 to the 20 is, I cannot do calculation now, but I think it's feasible, 2 to the 20. Okay, so just give you a rough idea, and you need to estimate this from data, and the size grows really fast when you have more features. All right, and then the testing phase, you really just look up. You look up for that specific combination in your test data. You look up what is that one from the yes class. It's really generative model, right? Sorry, it's really this model. Yeah, here. So what is the px from yes? What is the px from no? all onto the CL class. That's exactly what you're calculating from the generative model. Or in this case, the generative model is the lookup table. And this is the simplest ever discrete generative model. But clearly, this is not feasible to this. Yeah. So this is just discrete random variable, right? Okay, I think here it's almost I'm repeating what everything I covered before. Now,